Thank you so much. I'm really excited to be here. Any excuse to come to London. I always love visiting London. All right, so I'm going to be talking about how Kubernetes is a platform for building platforms. And here we have a picture of a platform on a ship. Because anytime you do a presentation around containers, you need to find a lot of photos of containers. And I'm kind of sick of it, but that's kind of the world we created. All right, so let's see. Oh, I got to turn on my clicker here. Let's see, there we go. All right, so at heart, I'm a platform builder. I started my career a long time ago at Microsoft working on Internet Explorer. And you can laugh. But one of the things back then, I think, is that we were seeing this evolution of the web from being something that just shows documents to something that became a programmable platform. And so really sort of in my DNA, even from sort of the first parts of my career, that idea about building things that other people can use to build other things. And I think that for me, the mark of a successful platform is that people are able to take what you did and what you built and take it in directions that you really never predicted when you first started out. And I think Kubernetes definitely, for me, has hit that mark. And that's pretty exciting. After working at IE, I made the jump to Google, worked on Google Talk, which we also viewed as a platform at the time. It didn't quite work out the same way, I think. But we're still seeing messaging actually start to evolve in terms of applications on top of that also. And then went off and started out and built a compute engine at Google. And after getting compute engine up and running, we had this problem where the platform that Google used internally, the system called Borg, I'm going to go into a little bit of detail there, was pretty different from what the rest of the world was using in terms of VMs. And so we built something that was as much as possible palatable to real users and customers. But anytime when you're doing something like this, you want to make sure that you're eating your own dog food, as they say. You want to make sure that the stuff that you're using and that you're building on top of is the same thing that your customers are using and building on top of. And so one of our big goals was to try and sort of converge these things and have the experience for end users, or at least customers of Google Cloud Platform, be the same as the experience for internal users. All right, so let's rewind the clock a little bit. The platform that Google used is this system called Borg. And I think, have you all heard about Borg? Has this been, OK, so it's part of and it was one of the things that inspired Kubernetes. But before Borg, there was actually another system at Google called WorkQ. And that was really built as a system to manage MapReduce. So for those not familiar, MapReduce is, and there was a paper on this that was super influential and sort of launched some of the work with Hadoop. But WorkQ was really a way of taking batch processing through MapReduce and running it on a pool of computers, and then having different teams actually be able to submit jobs and actually run through those. And there's a rich history of batch systems for doing similar types of things. Google built their own. But after running that for a while, there was an idea that we wanted to, I wasn't involved, so the royal we at Google, we wanted to make sure that we could actually use everything more efficiently, so get more out of the machines that we had, which means being able to deal with noisy neighbors and all the things that happen when you try and pile a lot of workloads onto a single machine. And we wanted to do more than just batch workloads. We wanted to do serving workloads also. And there's subtle differences between how you actually deal with those in terms of assignment and scheduling and those types of things. And so that's really the stage that was set for Borg. And it turns out that even after Borg was in production and everybody at Google forgot about WorkQ, as these things do, the WorkQ APIs actually lived on probably for another 8 or 10 years after Borg was actually introduced. All right, so that was the sort of the internal platform that Google used. And again, the angle that Google was taking here was really one of let's use every part of the cow, right, or buffalo, or computer, or whatever, and so really driving towards efficiency, and in doing so, introduced technologies like C groups that actually became one of the sort of basis technologies for containers. As we introduced Kubernetes, though, what we found is that folks came at Kubernetes from a different direction. The real, I think, motivator for so much of the excitement around containerization, around orchestration, is really about API-driven workflows that these things enable. It's about enabling teams to move faster in a self-service way, and the benefits around efficiency of being able to pack things in. It's very much a nice to have, but those things only manifest themselves at a scale that only a fraction, I think, of the user base really can appreciate. All right, so what is Kubernetes? All right, so it's an orchestrator. We all know what that is. Well, maybe. I think a lot of folks nod their head and say, okay, yeah, I know what this is. But I think it's worth really looking at what are the problems that we're looking to solve here. So fundamentally what we have is we have a pool of computers. We call that a cluster. And we want to use an API to say, I want to run this workload on this pool of computers. Find some place to run it. And then this system automatically takes care of actually assigning a workload to a computer and keeping it running. The next step from that is, well, I just don't want one of these things. I'm internet scale. I need like 10 of them, right? Or I need 100 of them. I need 1,000 of them. And so there's a bunch of primitives that get built up in Kubernetes for being able to scale these things out. But once you start getting dynamic in terms of how you place and how you manage these types of things, there's other problems that you now need to solve. It gets complicated from a networking point of view. You need to have service discovery. How do you start dealing with storage? And so this is where things really start to get interesting, because once you sort of introduce this sort of API-driven dynamism around this, there's a whole bunch of new problems that you have to solve. And I think that's really where the interesting stuff starts to come in. All right, so what is Kubernetes really? So at its core, from an architectural point of view, Kubernetes is really a database. It's a database that actually keeps track of where you want to, what you want to run and where it's been assigned. And then in front of that, we actually have a bunch of logic. And that logic both implies policy around who can actually modify what, being able to track these things, being able to implement that logic of placement, scheduling, replication, that type of stuff, all gets built on top of it, but all of it actually gets funneled through this fundamental database. And so here is my beautiful artwork around a simplified sort of block diagram of what a Kubernetes cluster looks like. And it's not in the center, but in the center you actually see, here's the database, etcd. So etcd is a highly consistent database. It's similar to those who have used it to Zookeeper. There's other systems out there. This is actually based on largely based on a paper published by Google around this system called Chubby internally. But the only thing that talks to etcd is this component called an API server. And that's that policy engine that actually presents sort of a more semantic interface to the database. And so, again, that API server will do things like authentication, authorization. It'll actually do some schema translation for versioning. It'll go through and actually throw off audit logs. So all sorts of sort of standard API gateway type of stuff actually gets implemented in the API server. What you'll also notice here is that everything interacts to the API server through APIs. So there is no cheating. There are no components inside of Kubernetes that get special access directly to etcd. One of the great benefits of this is that it's possible to swap out a lot of these components and have Kubernetes continue to work. And so if you take a look at something like the scheduler here, so the scheduler is the component in Kubernetes that actually makes that decision of where to place a particular workload. You can swap that out and write your own scheduler. People have done it in Bash. And it's just a matter of interfacing with the API to essentially do that piece of work. All right, so what we have here, let me just run through things real quick. If we have these set of components here, collectively we call those the control plane. Oftentimes they can be put on a single machine or they can be replicated across three machines or even more for a highly availability setup. Sometimes people will run etcd on the same machine. Sometimes they'll run it on a different machine. This type of flexibility for being able to bundle and unbundle these things is actually one of the things that lets Kubernetes both work small but also scale up. We kept some of the core control plane services as separate processes. So these are actually separate containers or processes that run as a way to keep ourselves honest, to make sure that we weren't actually doing that cheating and having these things talk directly to etcd. And so the scheduler is that component that makes those decisions of where to place things. And then the controller manager contains all of that logic that implements the replication, the service discovery, all of that stuff happens with inside the controller manager. Now, we could have bundled all these things together, and there are projects that kind of smush all this stuff together. But this is typically how these are deployed. Over time, we're working on breaking more stuff out of the API server, because there is some stuff that did get built in, specifically integration with various cloud providers will probably be another block in this diagram very, very soon. All right, and then each of the nodes, each of the worker nodes actually has this server called a kubelet on it that essentially is that bridge to the API server and provides the interface between that and the container runtime. In this case, I have Docker up here, but there's a standardized interface that you can swap in other container runtimes. And so the name kubelet, just a little bit of history with Borg, the sort of the agent that runs on the machine was called the Borglet. So this is kind of a Googleism. There was a successor system to Borg called Omega, and so Omega had the omelet. That's a really, really bad joke. And so kubelet is just a Googleism. I think other folks might call that the Kubernetes agent, but kubelet's a cute name. All right, we had a bunch of interns at Heptio, and they called themselves the kubelets. So yeah. All right, so that controller manager brings in this idea of a controller. So this is the core piece of business logic within Kubernetes. And what a controller does is for any particular object in the Kubernetes system, there's a standardized API, and as part of that API, you have a desired state, what we call spec, and then you have the actual state of what's happening, what we call status. And the job of a controller is to take a look at the status or where the world is and actually try and move it closer to that desired state, to that spec. And so it's really so I went hiking a little while ago with my kids down to the bottom of the Grand Canyon. It was an amazing experience. The thing about hiking the Grand Canyon is that, down is optional, up is mandatory. This is what they say. So you get to the bottom, and that's kind of the easy part, and then you have to climb your way out. And so there's this refrain when you have, smallish kids, and you're trying to push them out of a big hole in the ground, is, it's just relentless forward progress, always one step in front of the other. And that's what controllers do. They take a look at the world, they take a look at where they want to go, and they just try and make some forward progress to actually try and bring these things together. And in doing so, we actually can, it's a very stable sort of distributed systems paradigm to be able to do this. And I think a lot of times with Kubernetes, we talk about the idea of edge-triggered systems versus level-triggered systems. This is what we call a level-triggered system. In an edge-triggered system, the idea is that you see an event, you react to that event. Oftentimes, it leads you to have state machines that you actually run yourself through. State machines can be great, but they're also very difficult if you find yourself in situations that you didn't foresee with your state machine. And that's where a lot of those difficulties come in. Also, if something crashes and you need to catch up, you need to actually be able to manage processing all of the intermediate events to be able to run your state machine forward. On the other hand, a level set triggered system like Kubernetes, it's really like, I don't care about what happened in the past. All I care about is what is the current state and where do I want to go and how can I make forward progress. And so if something unexpected happens, if something crashes, you don't have to actually manage dealing with all the events that happened in the past. It's just a matter of taking a look at the world now, taking a look at where I want to go, and making relentless forward progress. All right, so what does this look like as these different components inside of Kubernetes react with each other? So I love sequence diagrams. I think they're amazing. So this is sort of the simple flow, for how a pod gets scheduled. So a pod in Kubernetes is essentially just here pod, think container. I'll go into a little bit more detail in a bit. So the user goes ahead and creates the pod, and sends that to the API server. The API server writes that to etcd, and then everything returns to the user. And so there's some validation to make sure that you didn't specify something that's grossly incorrect. But in general, there's no guarantee at this point that the pod will go ahead and get scheduled. At this point, the scheduler then notices that there's a new pod that hasn't been assigned to any node. It then goes ahead and makes its scheduling decision. It has a bunch of state cached in RAM about the state of the cluster so that it can actually make the decision of where to place this pod. And then it actually writes that decision back to the API server that then writes it to etcd, and then everything returns. Finally, the kubelet notices, hey, I have a pod that's been assigned to me. Let me go ahead and start triggering actually running that thing, essentially called Docker run. And then as that pod comes up, I want to write the status back into the pod object so that folks can actually be apprised of what's going on. And so the interesting thing here to look at is that none of these components actually interact directly with each other. Everything actually sort of gets laundered through the API server. And this is one of the keys to the extensibility of Kubernetes. All right, so one of the things that you may have seen there is that this component notices that something changed. So this uses a capability built into systems like etcd or Chubby or Zookeeper, this ability of let me know when these particular sets of rows in the database change, or this part of the namespace in etcd changes. That type of capability to be able to react when somebody writes, I get a notification, is critical for the performance of Kubernetes. Now, Kubernetes would still run without this, but you'd actually start doing polling loops, and it would be slow, and it would generate a lot of load on the systems, and so it would limit scalability. So this idea of watch is built into etcd, and then it gets reflected out through the API server. So one of the fundamental things beyond sort of like get and list and set, all the sort of RESTful operations that you would expect in a API, is this idea of watch, which is like, let me know if anything changes. And watch is not quite the same as something like putting an event in a Kafka queue or some sort of pub subsystem. What watch is let me know that it changed, maybe actually let me know what the changes were, but if I miss one of these updates, the idea is I don't care about all the events that happen in between. I can go ahead and resync, find the current state of the world, and then actually keep current with that moving forward. And so again, this is very much a level-triggered concept versus an edge-triggered concept that you'd often see in event-based systems. All right, so we use the term orchestration a lot. And for me, when we say orchestration, that actually brings up the visual of an orchestra with the conductor, and they have the score that has everything planned out, and everybody has to play their part exactly, and it's all planned from the beginning. But anybody who's dealt with any sort of computers at all, we know that computers, we like to think they're deterministic, but they're really not. Especially when you start having a network of computers, especially when you start having them talk with each other, when you have external input coming from users, hardware failures. What we find is that the behavior of these things ends up being emergent. You can't plan it all out from the start. And so the interaction of these different components, these different controllers with each other, in my mind, I think is a lot more like jazz improv, where you have a bunch of players that are listening to each other, reacting, and playing based on what the other players are doing. And for me, that's, I think, a much more descriptive analogy than orchestration for what systems like Kubernetes are doing. All right, so that's a little bit of sort of Kubernetes architecture 101. I'm going to start talking about some of the nitty-gritty details of these particular objects. And now this may be a little bit of, for those super familiar with Kubernetes, this may be a little bit of old hat. Hopefully you don't mind me, you'll indulge me here. One of the ideas as we built Kubernetes out was this idea of layering. I think another way that we think about this is Unix philosophy. We want to have a bunch of things that you can reason about that are relatively simple, that build on top of each other to actually create more and more complex behavior. And so at the sort of core sort of primitive that we have with Kubernetes is this idea of a pod. I talked about that earlier. It's a slightly different concept from a container. In fact, a pod can contain multiple containers. Yes, contains containers. A pod can have multiple containers, which was controversial when we first introduced Kubernetes. But with the advent of things like service meshes, this idea of having a sidecar container ends up being, I think, fairly useful and well understood at this point. So the difference between a pod and a container is that you can think of about a pod as sort of a claim to a set of resources on a machine, including networking, disk, and compute resources. And so that's essentially the footprint on a machine, which is the thing that the scheduler actually cares about. How much of this particular machine is this particular workload going to take? And the idea that if you want to run a bunch of containers together, if you want to start worrying about local storage, those types of things all get bound up in that scheduling decision for the pod. All right, so building on top of, okay, so a pod lands on a machine, lives and dies on that machine. If the machine dies, the pod actually dies also. This is an important concept because in distributed systems, something could disappear and then show up again. And if you actually took that identity of a pod and recreated it someplace, you might actually have two of them running on two different machines at the same time. And so that's, hilarity ensues when that happens. So, but what that means is some of the resiliency that we want out of a system like Kubernetes, you're actually not going to get that with a pod. If you schedule something and then that machine dies or disappears, like there's nobody, without building a different system that's actually going to go ahead and make sure that your application continues to run. And so that's where the idea of a replica set comes into play. So replica set is one of these controllers, and it's actually conceptually very, very simple. I have a template for a pod, and I have a count on the number of pods that I want to have for that. And so the replica set looks up, says, how many pods do I have? Let's say it's supposed to have 10. Oh, I only have 8. Let me go ahead and make relentless forward progress, and I'm going to create 2 more pods to actually be able to try and drive my actual state to my desired state. Similarly, if the replica set wakes up and says, I have 12 pods, but I really only want 10, it'll actually pick a couple of pods and kill those, delete those. Now that might happen when you're scaling down, but it also might happen in one of these situations where you actually have a machine disappear and then show back up. It may find that wacky things happen in distributed systems. This is one of the ways that this deals with it. That's a very simple type of controller to be able to reason about, to look at this. Now, there's some subtleties here. You don't want this thing to react too fast because if you do, you can, there's a whole bunch of control theory around this, around sort of hysteresis, where you're actually overreacting and overshooting. But I think conceptually it's very easy to reason about what a replica set does. Now, layered on top of replica set, we have this idea of a deployment. So replica set doesn't know about versions. And you can play some games where it's like you change the template out from under the replica set, delete each of the pods, let the replica set replace it, and you can actually do an upgrade that way. But it's up to then the client to be able to do that. And often you want to do that over a long period of time. You could do it from your laptop, but we all want to avoid sort of magic laptop syndrome where it's like this is the one machine that has all our deployment secrets and scripts on it. And so that idea of being able to do an upgrade perhaps over a longer period of time, that gets encapsulated into a new controller, a new type of object called a deployment. And so what a deployment does is just like a replica set manages a set of pods, the deployment manages a set of replica set, one replica set per version. And typically, for a rolling upgrade, it'll actually create a replica set for the new version. It'll turn up the number of replicas on the old version, and meanwhile, turn down the number of replicas on the old version. And so in doing so, essentially affects a rolling upgrade. All right, so this is all serving workloads. We talked about, though, that Borg was originally inspired by batch for MapReduce, and Kubernetes is inspired by Borg. And so what about sort of, batch one-shot types of things? And so we have this idea of a job. And so most of the time, we set up the options on a pod to say, keep this thing alive no matter what, right? That's what you want with a server. With a job, it's like, hey, I want to run this thing to completion. I want to run this until it's successful. And so it's a different way of using a pod. So a job manages pods just like a replica set manages a pod, but it manages them in a different way, aiming for essentially a batch computation type of thing. And then layered on top of that, we have, of course, a cron job, which is essentially a simple controller that just takes care of launching a job at a specific time. Now, it turns out that as an example, one of the things we try and do is keep these things as simple as possible. Cron job does not support time zones. because time zones are really, really hard, and they change, and they're sort of a political construct. Multiple times folks have said, hey, let's add a time zone to cron job. And we said, hey, we're not so sure about that. That gets really complicated, unpredictable, what happens during daylight savings time, all that. So we try and keep these things simple. But that's not to say that somebody couldn't actually build on top of this, using extensibilities and mechanisms built into Kubernetes, some sort of time zone aware cron job that then runs cron jobs and sort of essentially creates another layer on top. All right, so this gets to this idea of custom resource definitions. All of the objects that we've talked about so far are built into Kubernetes. The logic for those things are built into the controller manager, and those schemas are actually built into the API server. But as we started building Kubernetes, we recognized that having these things be locked in is slowing down people innovating, and actually as we're missing out on the opportunity of actually reusing a bunch of the plumbing that we built for Kubernetes for other types of processes. And so this is where one of the co-founders of Kubernetes actually started really pushing this. This was Brendan did this. It was originally called third-party resources, got renamed to custom resource definitions, or CRDs. This is the idea of you can install new schemas into a Kubernetes server. So just like Kubernetes has replica sets and deployments built in, you can actually go ahead and create your own objects, write your own controllers that act just like those that are built into Kubernetes. And so this is the key extension mechanism for Kubernetes. And it's one of the things that I think really starts to make Kubernetes that platform for building platforms. And we've seen all sorts of systems building on top of Kubernetes using these mechanisms. I think some of the ones that I think folks may have heard about the most would be things like Istio uses a lot of CRDs, Knative, which is sort of a serverless toolkit that's being built on top of Kubernetes. I believe Kubeflow does also. So all sorts of interesting stuff uses CRDs. All right, and then you all have heard this term operators in terms of a piece of code. I don't know if there's an official definition. I'll give you mine. When I first heard about this concept, I said, oh, that makes sense. Computers used to be people also, right? So operators are a piece of code that essentially takes a lot of the logic around operating a complex system and puts that in code behind an API. The idea here being that in the fullness of time, there's no reason why we couldn't use something like Kubernetes to build an RDS-like system. I think when we look at something like AWS, one of the best services and one of the sort of keystone services are the managed database services in AWS. And the reason being is that managing data is really hard. I'm not smart enough to do it. And it's the type of thing where you really want a lot of expertise. And so being able to say, hey, I want to make this the problem of this system. I want it to be fully managed. That's a real service, and that's something that folks really value and will pay for. Now, the only way that Amazon can make that happen and can make that scale is to take all of that knowledge on how to operate something like a MySQL database. What happens when a machine fails? How do we do upgrades? How do we do backups? Take all of that and actually write code to automate that stuff and then put it behind an API. So the idea of an operator is to take that very idea, but actually make it such that we can have a set of third parties. Anybody can build an operator on top of Kubernetes that starts to deliver that type of fully managed experience. Now, we're not there yet. We're still very much early days here, but we have the tools that we need to be able to build that type of experience. So as an example, Oracle does have an experimental, it's very early again, operator for MySQL, built on top of Kubernetes. And just like the layering discussion that I had earlier with the built-in objects, they've gone ahead and actually layered the objects that go into their MySQL operator. They have a MySQL cluster. They have I got to look at my notes here. They have a MySQL cluster. They have which has sort of the set of parameters for the number of replicas, whether you want to be in HA mode. They have a MySQL backup, so that you can actually create a backup will actually cause the backup to happen. They have a MySQL restore, that you can actually API drive, restoring a cluster from a backup. And then they have a backup schedule, because doing this on a timeline is a very common operation. And so you can see in that way, they've built these layered set of objects using CRDs, taking in that domain knowledge of what it takes to manage something like a database, and then built that on top of Kubernetes. All right, so building a controller is kind of a pain. It's much harder than it should be. For me, one of the most exciting things that we're seeing is that there are a set of toolkits and systems that are making it that much easier to build an operator. So one of my favorites is this thing called Meta Controller. It essentially takes common operator patterns and makes it so that you can sort of insert a little bit of code here and there and make it happen. So you can like Kubernetes doesn't support blue-green deployment out the gates. It's not built in. But you can create a blue-green deployment object using a custom CRD and a controller with Meta Controller and about 150 lines of JavaScript. And so I think this is the forefront of making this stuff much easier to use, much more accessible, so that you can start building up some of this automation. And yeah, but there's other projects out there too. I think there's one called Operator Kit. There's KubeBuilder. Both of these have the aim of making it easier to actually start activating these patterns that I'm talking about, so that we can start applying them to more and more domains. All right, and then this goes beyond Kubernetes. I think this is what's really interesting for me, is that a lot of times we think about, I do a bunch of stuff, but it all ends with pods in the end. But I think what we're finding is that you can use these distributed system patterns, this level set goal seeking, the Kubernetes sort of API infrastructure to manage all sorts of other things. So a quick example would be that the AWS folks have an operator where you create a CRD that then goes ahead and causes it to actually call the AWS APIs behind the scenes. And so they're essentially taking the AWS APIs and then actually surfacing those things up as native Kubernetes objects, with all the benefits that come with that in terms of being able to automate those, playing into the Kubernetes authentication, authorization, that type of thing. Folks use this for automating configuration of a load balancer, right? Whether it be a software or hardware load balancer. I think this is the example of something like Istio. You're using these systems to be able to manage essentially the control plane for the service mesh. And it goes beyond just sort of like DevOps-y types of things. I've talked to companies that build controllers that start to automate human processes. And so you may have a CRD for essentially a development team at your company, whatever that means for you. And you can say, well, for every team, I want to make sure I have a Slack channel. I want to make sure I have let's say, a Git repo someplace. I want to make sure that I have my CI/CD system provisioned. You can drive all of that provisioning based on these types of concepts. And so if somebody accidentally deletes the Slack channel, it'll automatically get recreated, that type of thing. So highly available Slack, right? That's an oxymoron, I think. All right, so what does the future hold? So for me, I think it's really, really exciting to see how Kubernetes, which was built with this idea of let's just keep some containers up and running, let's look at this solely through the lens of orchestration. How do we take sort of the platform that's been built there and automate it with higher and higher levels of abstraction, but also use it as a base to be able to run controllers that'll automate other things? And so viewing this as essentially a distributed system runtime for doing all sorts of types of distributed systems, for me, that's the really, really exciting future for Kubernetes. I think the original definition of platform that I talked about of being a set of building blocks that people can put together and take it to places where you never saw it before, I think this definitely is something that we didn't really foresee this when we started the Kubernetes project. And so yeah, so I think that is the most exciting thing for me, and I think we're still, again, very, very much at the beginning of where this is going to go. Having this sort of substrate for building distributed systems, I think, is going to really hopefully ignite a really vibrant ecosystem of folks building new systems on top of it. All right, so with that, thank you very much.